Cox is not Pierre Friedlichstein, since he didn't make it out of Europe.
No. He's much better looking. And he's got one of those pointy things.
Different accent. So, Peter Cox is going to tell us about the status of carbon cycles. Could go into AOGCMS.
Right, okay, thank you. Yeah, so I've taken over from Pierre here. He sent me through his slides, but I've rewritten quite a lot of it because there was much too much of his model and not enough of mine in it. So. But don't tell him. It's his fault for not being here. I just want to kind of go through where we're at with regard to specifically the coupled climate carbon cycle model into comparison project, the status of the models, and where I think we'll be by AR5, what the implications are. So we'll start with the rationale for, this is the plug. This is why the carbon cycle has to be part of Earth system models, which is that we've got lots of evidence of strong feedbacks between, or strong interactions at least, between the carbon cycle and climate. And then I'm going to talk about the current status, specifically the results that have come out of this project called C4MIP, the robust findings, there are one or two, they're mainly qualitative, and the uncertainties, and they're very significant, and the missing processes. Now these missing processes will be addressed, many of them, not all of them, many of them will be addressed in the models that were likely to be ready by the time of AR5. And I'll go through some of the key things that I think we sort of have to do in order to be credible by AR5. And one or two things that it would be nice to do, but maybe ambitious. I mean, model development, you always set your target and then gradually reel it back into reality as time goes by. Okay, first thing of course is that the carbon cycle is playing a big part in mitigating climate change at the moment, with only about 50% of our emissions remaining airborne and the rest being absorbed by the ocean and the land. You'll notice, although you probably can't read it all that well, but there are quite large uncertainties in these figures, particularly the land one. But the best guess is that roughly a quarter is being absorbed by the ocean and a quarter by the land. So that means half of our emissions are going missing, and there's been kind of an assumption that things would remain that way, that we'd get this mitigation for the carbon sinks, and that climate change would continue to go at half the rate that we're really due in a way. But that's a dangerous assumption, as I'll explain. Okay. We also know, and I'm going to give a bit of evidence of this, that atmosphere, land and atmosphere ocean fluxes of CO2 are sensitive to climate. In fact, ocean and land stores of carbon are sensitive to climate on all sorts of timescales. The most obvious one is here. This is the glacial interglacial cycles, and I'm the first person to show this. It's amazing, isn't it, on an Earth system workshop. I'm sure I won't be the last. Showing this very strong correlation between temperature and CO2 that can't be accounted for because of the lags and because of the timing of these cycles by just the effect of CO2 on temperature. It has to be the effect of climate change on CO2 as well. So we know that on the longer time scales, you know, tens of thousands of years, the natural carbon cycle is responding to climate.
Ever removed stuff so that
Sorry?
it's easy to use this?
No, it's okay. I like to move around. Keeps me awake. And this is on the much shorter time scale. So this is the famous Mauna Loa record of CO2. And I show this for two main reasons. The first one is, of course, this seasonal cycle is indicative of uptake in the northern hemisphere vegetation during northern hemisphere summer. And so you get this cycle that's very clear. And also you get variability that you can just about see through the red line, which is the annual mean. And that variability is, in fact, strongly correlated with climate variability. This is the annual CO2 growth rate for the Mauna Loa record from 60 onwards. And you can see a lot of variability in it. An upward trend that is largely due to increasing fossil fuel emissions, but the variations are bigger than the trend. And those variations are predominantly due to the land's response to El Nino type events, well, in fact, El Nino events. So this, if we detrend this growth rate, and apologies for the, can you see this at the back, Dave? Probably can't see it at all. This is the anomaly, so take out the trend, the CO2 growth rate showing these large peaks during El Ninos and the tendency to have slower than average CO2 growth rates during La Ninas. So we can see, even at the interannual time scale, that climate change is influencing carbon uptake significantly. And there are examples where this doesn't quite operate. So here's the the fit now. This red line is the fit to the ENSO signal, to the Nino 3. With El Niños being periods when we get larger CO2, and La Niñas periods when we get lower CO2 growth rates than usual. And wherever we get anomalies, they're associated with the cooling associated with volcanic events. So we can see it's not just some sort of correlation, but some non-climate related correlation between ENSO and CO2. It's actually a response to climate, because this perturbation here, for example, at Pinatubo, very significant associated with the cooling of the climate. Okay. So on all sorts of timescales, we can see that the carbon cycle responds to climate. And we therefore have a good chance of there being feedbacks associated with climate change affecting CO2, feeding back on climate change. But to date, most GCMs have neglected that, and that's really because of the practicality of trying to include this. And the question we have to ask ourselves is, how important is that? So this is just a flow diagram of where we were in the TAR AOGCMS, the third assessment report, so around 2000. In most cases, CO2 was calculated offline by simpler carbon cycle models, and ignoring the fact that climate change would have a direct impact on uptake by the ocean and by the land.
Actually, that's not true. I mean, those models do have that in them. It's uncertain.
Sure.
And they were tuned to give, sort of a central result.
Yeah,
so
they
it's not
did it
fully consistent, but it was.
Yeah. Okay. So there was some account taken of global feedbacks associated with temperature in some of these models. That's true, but the regional patterns obviously can't be dealt with in global carbon models. And largely speaking, these models dealt with CO2 effects on land and ocean, and the feedback on the CO2 growth rate. And that's where we were. What we've done in the fourth assessment report through this C4 MIP project that I'll talk about in a minute is to close these feedback loops from climate to ocean and land uptake. And that really means taking account of the effects of climate change on plant productivity and soil respiration, the two main fluxes in and out of the terrestrial biosphere, on the solubility of CO2 in the ocean, on vertical mixing through stratification, which might suppress vertical mixing, and possible change in ocean circulation. And the thing to note about this is that whereas before we were prescribing CO2 scenarios, in these coupled models, these first generation coupled models, we're now prescribing emissions. But in this first generation, these are the combined emissions of fossil and net land use. So we aren't dealing consistently with land use change emissions in these models. And that's one of the main things we'll have to do for AR5.
So how many of the models use the dynamic vegetation in C4?
Most didn't. I think probably 3 or 4 had dynamic vegetation in them. It seems on the century time scale, the dynamic vegetation doesn't have an enormous impact. I mean, the timescales for forest migration, for example, are really rather long, in these models at least. The timescale for forest dieback is short, but you don't need to know the forest is going to change its nature to do that. You just need to know the forest is going to decline. So the veg dynamics doesn't have an enormous impact in these models. George will surely disagree in the next talk. I'm going to show you the results from the Hadley Centre model, which was the first one to be published, but was very close to being published at the same time as the French model. And I'll show this because it gives you an idea of how large the effect might be. This model gives the biggest feedback, okay, and all the models give a positive feedback of positive climate carbon cycle feedback. This model gives the strongest, and the response is largely a land response. So I'm going to run that again because I was talking when I was. And these are decadal means relative to the initial. So what we're seeing here, where we've got reds and yellows, is where there's been uptake of vegetation in this case and soil carbon. When we've got blues and greens, we're seeing a net release relative to the initial state. So the things to note are that by the end of the simulation period, we've got net accumulation of carbon in the high latitudes, increased growing season length, and CO2 fertilisation of growth are responsible for that. And in the tropics, we tend to get losses, particularly in the Amazon basin, where we get a significant drying in this model. And there's drying in other models as well, but certainly not in all of them. The soil carbon shows a much more general response to decline, and that's because there's an underlying assumption practically in all models, that warming will enhance soil respiration rates. And although the input, the litter input from increased growth will go up, which will tend to increase soil carbon, temperature will eventually overwhelm that in these models. And that's common to all models. It's not as large as this effect, but it is basically occurring in all the models. And on the right-hand side here, if you can see it, is the impact of that on the CO2, on the temperature, and on the soil and vegetation carbon. And so initially we get accumulation in both soil and vegetation, and then we reach some critical point where the climate effects, which are tending to reduce carbon storage, overwhelm the CO2 effects, which are tending to increase it. You get loss of carbon from the land, you drive up CO2, and you drive up global temperature. And in this case, it's a very big change. It's 200 parts per million in this model, more by 2100. Other models are in the range 20 to 120 or something, with a mean around, roughly around 100. So all the models are showing a positive feedback, but some of them are rather small. The smaller ones, you probably wouldn't bother going to all this trouble to model. Yeah, of course.
What's the major reason for the abrupt change, the decrease of the soil? Does that depend on parameterization, critical parameter or parameterization, or in the process?
It depends. All of these things depend on the details of how you parameterize, but basically you tend to see this because there's two things. The inward flux, the net primary productivity, is saturating with CO2, and it's also tending to decline with climate change, especially in the tropics. Okay, so the net primary productivity goes up and comes down, which has a tendency to drive the veg carbon first up and then down. And then there's the additional thing that the soil carbon is coming out faster because of increasing temperatures and drying in some regions. So the soil carbon hits this threshold sooner. It's got a declining input and increasing output at the same time. Okay, yeah.
Have observations in the lab or in the field in relation to the soil temperature borne out this rough pattern?
You can't do it globally, of course, but generally speaking, they show a response of soil carbon, of heterotrophic respiration to temperature. Okay, generally speaking. There is an issue about how long that lasts. Ultimately, what would happen if you didn't have inputs going up is you just run out of soil carbon, and there would be a kind of acclimation because the fast decomposing layers would just get burnt off. We don't see it in these models, but this model's had a rather crude soil model. We've put in a more complex one and we get a similar response. It's slightly smaller, but it's basically the same critical point. And I think, well, the biggest uncertainty here is actually the interplay between temperature and soil moisture. If like in this model, the soil moisture regime and the temperature both enhance respiration, and soil carbon will go down. In some models, they tend to counteract each other. Sorry, yeah.
Sorry, we might have
Yeah.
said this.
Yeah.
How is this run done in terms of starting off? No, but you started with some emissions scenario.
We started with 0 actually, so we run the model up to a sort of pre-industrial 0 emission state, a sort of artificial 0 emission state, with vegetation dynamics. So to come back to the point Ron was making earlier, we have to deal with things like the forest doesn't look exactly like it should, although there is a forest there, but it's not quite as large as it should be. So some of the things are to do with initial state, but not many of them actually, I think.
But the point is, so this is without assuming any change in human-induced increase in CO2 from our actual activities. This is just the effect of the interactive vegetation.
Yes, this run here, so this is the difference between the run with and without the feedback in, and the dotted line is essentially a prescribed, it's a prescribed CO2 run, a prescribed CO2 concentration run.
Where'd you get that? Where'd you get that emission?
It's a standard one that was used. It was an old emission scenario. It's a standard one that was used in
IS92.
A. So it's, we're going to talk about SOS A2, which is slightly larger emissions, but this was the first run we did with these old emission scenarios. Okay.
Some of the regions show increase of soil carbon.
Yeah, the high latitudes.
What makes those regions so special?
Up here, you mean? Here.
Yeah, or down there.
Well, I think in the high latitudes here, there's growing season length is increasing because of the warming. So the increased input from net primary productivity is beating the increased respiration, right? And so that's what you're seeing there. In these regions, I suspect it's a moisture regime change. I haven't checked, but I suspect there's more rainfall and probably net primary productivity has gone up as well there. The opposite's true in these regions where we've got reduced rainfall. No.
Peter, is there fire in that model?
No. So this is purely climate effects on primary production and heterotrophic respiration and veg dynamics. But the veg dynamics in this model is not a significant player, I think.
Is heterotrophic respiration just a function of warmer soil emits more CO2?
That's the main thing. It's in this model, it's basically a factor that's related to soil moisture. So there's a peak in soil moisture. Basically, if you haven't got any oxygen in the soil because it's waterlogged, you're not going to get much respiration. But if you're down on this bit of the curve, then as soil moisture goes up, you tend to get more respiration. And as temperature goes up.
A certain amount of organic matter that's in the soil and it just starts.
Yeah, sure. Now, there's a lot of debate about this, although some of it, I think, is a misunderstanding of the difference between the control experiments that people do and what you're doing in models. If you fix the litter inputs like you do in an experiment, then every one of these models would, as people call it, acclimate. They'd burn off enough carbon so that the respiration flux balanced the litter input. And there's a kind of bogus argument going on between the experimental community and the modelers, which is just a misunderstanding about that boundary condition, really. Some of it's real, but mostly it's bogus, I think.
What about the ocean?
Yeah.
I mean, the temperature of the ocean is changing. So
Sure.
in
Sure.
particular, for example, if you slow down of the thermohaline circulation, do you have because you had some quite large impact on the ocean at the end of the run.
What we generally find in the model, in the C4MIT models and this one included, is that the ocean response to climate is not a significant player in this generation of ocean models. The difference between the individual ocean models' response to CO2, in other words, the fraction of emissions they take up, is a significant uncertainty. But it turns out that there's a sort of counteraction between the slight reduction in ocean uptake because of temperature effects on solubility and stratification, and more CO2 in the atmosphere because of land. So the ocean sink looks roughly the same. Okay, so having looked at the first couple of models, and I haven't shown Pierre's model, we mustn't tell anyone, don't tell him, and shown that these models were very different actually. I mean, Pierre's model is not so different as some of the other models that come out compared to that, but produced a feedback of order 50 parts per million rather than 200. Still a positive feedback. There was an initiative set up by IGPP GAME, which is now AIMS, and WCRP WGCM, to look at a more complete intercomparison of these coupled climate carbon cycle models. And we've now got to the stage where there are 11 of these models. 7 of them are AOGCMS, 4 of them are ENICs. So in this case, we've looked at global variables. We haven't been specific about the extent to which you have to resolve things spatially. The bottom line is that all models produce a positive feedback. They all suggest that climate change will mean more CO2 stays in the air, but the magnitude of that feedback varies a lot. And here's the CO2 concentration. So this is the model I just showed you with this very large feedback, you can see. And here's most of the models are down here, and 1 or 2 are down at very low levels. So what we're seeing is roughly, this is not an up-to-date plot, but roughly speaking, we're seeing a mean change of about 80. If you take the 2 outliers out, it's still roughly around about that, the low and the high one. So it's a big feedback on a CO2 increase that would be about 300 parts a million, sort of 25% feedback. And on the bigger feedback's much larger, of course, more like 50%. One of the big problems is that you can't use the historical constraint on CO2 well, the historical CO2 budget is not a good constraint on the behavior of models, unfortunately. Otherwise we could rule them out. So what I'm going to show you here is essentially the amount of emissions that are in the atmosphere, in the ocean, and on this diagonal taken up by the land. And you'll see the scatter that comes from the models, first of all up to the year 2000. And these are the models with letters on. And I can tell you which model's which, but it doesn't really matter. A lot of them are down here. They do a decent job of reproducing the airborne fraction. They sort of be the #1 validation. If you didn't do that, you'd think model's not right. But they do it by having very different partitionings between uptake by the ocean and uptake by the land. If you put in a kind of historical constraint on the ocean uptake and the emissions from land use, which are the biggest uncertainty, then you get a box like this. And this is not exactly right. The box is actually longer and thinner when I redid it, but most of the models fit in the box. The hope would be, of course, that these models turn out to have a similar feedback, but it's never that simple, is it? So that's the mean and range from the models that fit in the box, and then I'll show you in red the mean and range from the models that subsequently into the 21st century. So first thing to note is there's a shift in the mean here in the airborne fraction. More emissions remaining in the atmosphere means a positive feedback on climate change. Second thing to note is you don't rule out the outliers here. The models with the large and small feedbacks also fit in this historical constraint. So the historical constraint is rather weak on this, which is why we're all still in business. But only temporarily. And that's just to show that there is a rather robust tendency. If you plot the diagonals here, all the models go on this diagonal here, which basically means more CO2 in the air, less in the ocean, and less on the land, generally speaking. There are one or two that go vertical, which means that the ocean uptake hasn't changed very much, but there's generally a tendency for climate change to affect, to reduce ocean and land uptake, but mostly a land.
Peter,
Yeah.
Of models with similar land fraction uptakes, do
Yeah.
they agree on the mechanism for that land uptake?
Yes, I think so. I mean, pretty much all these
And then
models.
just follow-up question, is it the right mechanism?
Of course it is. Well, you know, there's no land use change in these models, so they're producing the carbon sink by CO2 fertilisation. There's no nitrogen limitations either. So the models have their responses to CO2 are similar for that reason. Their responses to climate are very different.
And at least in the case of the U.S., potentially all.
Yeah. I suspect there's CO2 operating in the US.
I'll see.
But the nitrogen
Different science operates in the US.
nitrogen limitation could change this quite a bit, though, right?
Yes, I mean, it does depend how nitrogen limitation goes. I mean, at the moment, these models are kind of assuming none, which would be consistent with us dumping so much nitrogen on the landscape that it doesn't make any difference. Or, and Dave might be able to comment on this, the possibility that increased decomposition in the soil will make more nitrogen available, which is a possible negative feedback on climate change. So they're sort of optimistic in that sense. They say, well, let's assume the CO2 sink just saturates with the kind of biogeochemistry of CO2, not nitrogen limitations. Otherwise, it would saturate sooner.
Are other nutrient limitations like phosphorus considered?
No, not in these models at all. And I suspect even by the time of AR5, we'll probably do nitrogen, but we probably won't get as far as phosphorus. And we might, I don't know what you think, George, would we have to in the tropics? We'd have to consider phosphorus?
Actually, the Australian group is working phosphorus into their
Yeah.
system on linking.
Yeah. I mean, there are...
I think it's nitrogen first and then it's phosphorus.
Yeah, I mean, I think it's... One of the points to make here is that some of these models do include nitrogen limitations, but by choice we decided to just look at this rather idealised experiment. Most don't include nitrogen limitations, including ours, but some do.
What about
Yeah.
using amplitude of seasonal variation for that kind of constraint?
Yeah.
Or its latitudinal dependence?
Yes, that's a possibility. Most of these models have been validated to some extent, but there's as yet no sort of standard hoop jumping done. We did intend to do what was called, as you know, C4MIP phase 1, which was just about get all the ticks in the boxes. But as is often the case, we thought, well, let's do the interesting bit first, and then we'll go back and check it. So some of these models have gone through some checks, not all of them. And you could rule one or two out already just by this, actually. Yeah.
Is the CO2 fertilization sort of the maximum CO2 fertilization that one might expect? Or
It's based on, I mean, I think the photosynthesis models are reasonably complex components of these, so they're Farquhar type models. They have a CO2 fertilization that's, I think, fairly sound and fits things like the Norby paper in terms of the face experiments, roughly speaking, sort of order 20 to 30% increase for a 50% increase in CO2. So a lot of the argument about models overdoing that, I think, is also wrong. But I'm a modeler, so I'm biased.
Does your evaluation look at processes, like on plot level? Do you you do evaluation of all those models?
We haven't done all of them, no. I mean, it would be difficult with some. Some of the models, for example, the ones in EMIX are very large scale, so applying them at the site level would be difficult. Most of the GCM models would have been tested against flux data, but nowhere near as much as we can do. And there's a lot we can still do with that. And to come back to your point, the idea of using atmospheric constraints on CO2 to get at internal parameters in models is just beginning to be explored through data simulation. And that's potentially very, very powerful. I doubt it will feed its way into AR5, but it ought to be in AR6 if there is such a thing.
So you may be getting to this in your talk, but I always see these C-format results presented like you've been presenting them kind of in these global kind of feedbacks. What about like regional, I mean, could you discern that these would make a difference in regional climate and patterns of circulation or things like that, or is that been looked at at all?
You mean the feedbacks would be important locally?
Well, if you run with and without carbon cycle, you see.
Well, that would obviously
patterns of climate.
That would obviously be very much GCM dependent, like any CO2 induced changes. I mean, they're essentially well mixed responses. There are vegetation feedbacks operating in the ones with veg dynamics, which tend to exacerbate the changes. But in terms of the CO2, it's just like the uncertainty you get from GCMs. You know, change the CO2 by 100 parts per million, you get a number of different answers.
Like in the GCMs, the emissions are coming out of the land in each location, right? So,
yes.
But then it just gets mixed pretty quickly.
It does. Now we did periods of these runs which we saved to do the validation, which we've got to get around to doing, which is to basically look at the historical period and what it implies about the way the seasonal cycle varies with latitude, for example, or where the source and sinks are. And we've got from inversion some estimate where the source and sinks are. And some of these models won't pass those tests.
The question always is, if you really want to know what the feedback is globally, maybe you don't care about the regional climate, you could just scale the patterns of regional climate change if you know the size of the carbon cycle feedback.
Yeah.
But maybe not. Maybe it does make a difference where the emissions are occurring and how that affects regional climate.
No, I don't think it does. I mean, I think the CO2 variation in terms of its radiative impact on climate will always be tiny. So in a way it's the easiest feedback to do, because unlike some of the chemistry where the regional patterns really matter and are very significant, with this one, you know, if you tell someone that you could take the climate change, you could do it asynchronously, take the climate change pattern, run a sophisticated ecosystem model and put it back, roughly speaking. The only issue is that you want to be able to do the water fluxes from the land surface and the carbon fluxes at the same time, and the water fluxes need to be done every half an hour, which is why we've ended up coupling up.
The question, you kind of locally went over it, but the thing I've never understood, why did you do the C4MIP2 experiment first and not the validation run against existing data? Because
some of the models,
a criticism that comes back to these results is, I don't believe these models, because you guys haven't shown that you've been able to do a 20th century experiment. Oh
no, we have. I mean, some of us have. Most of us have done it.
But you did it mostly after the C4MIP2 run was done.
Well, okay. This is a kind of validation, right? This is the zeroth order validation, which is, does your model reproduce the CO2 increase from pre-industrial to now? That is a validation that you would do first up. Then there's an issue about the regional pattern of CO2, like we were saying earlier, the seasonality of the CO2 in the atmosphere. Some models have done that, some models haven't. Some models would find it difficult because they've got coarse resolution, they're not GCMs. And some models just haven't got round to it. So we're in the same situation you might have been with GCMs probably in IPCC first report actually, which is let's do an idealized experiment and see what this bottom-up approach to modeling tells you. And then you go back and say, well, is this important enough to do properly? And it is.
The problem is these results are not presented, you are now, but typically when I've seen others present them, they're not presented as idealized experiments. You put the plot on the bottom that says 1900 to 2100 or whatever, and you say we're using a realistic emission scenario, whereas the couple GCM folks did the 1% per year CO2 run without the aerosols, which was known to be an idealized experiment. And I think that's where some of the connotation, and then which leads to a criticism for people who don't take the time to really understand precisely what you're doing when these results are presented, that you're overstating the case.
Well, okay. I mean, some of these models, for example, the Hadley model, we've run with much more sophisticated scenarios like aerosols, which turn out to be important. So if you have a strong carbon cycle feedback, you can imagine if you get your climate change wrong, you get your CO2 wrong by the current day. And what we therefore found is that unless we had appropriate aerosol forcing, we couldn't reproduce the CO2 up to the current day, which is interesting. It's indicative of the fact that it's got a strong feedback in it. So some have done more sophisticated scenarios, and it's a real difficult balancing act, this, because you really want to get a critical mass of a community playing before you really get hard on it, which is basically to say, let's get as many people involved in this as possible in order to just get the thing off the ground. We're in a situation where we had 2 models, you know, in the third assessment report, and it wasn't enough to even be able to make a statement about what those 2 models were saying, really. Just said, well, it's the range. And we don't even know how big the range is. We've got an idea of how big the range is now. It's big. Yes.
And this question about the ocean.
Yeah.
With respect to the ocean models, do you know how sophisticated is their ocean chemistry? Do they have ion balance for the different carbonate, bicarbonate ion, biological fluxes, phosphorus and nitrogen cycles
Right.
to the ocean itself?
They vary, and you may be able to fill in on this, but they vary particularly in terms of their ecosystem. Some models don't have an ecosystem, some have a diagnostic ecosystem, some have one of these NZDP type of 4-box models. And later models are now getting more sophisticated ocean ecosystems. I think the biogeochemistry is probably rather similar. I mean, they come out of the OCMIT models that cluster remarkably well, actually, compared to the land models up to the current day, and then do this afterwards. So I think the physical biogeochemistry, if you like, that is reasonable and probably fairly sound. Would you agree?
Yeah, and I don't think any of them includes ion feedback. Most of the current or in product run
Sure.
don't have that kind of
Yeah.
interactions.
And it's something I'm going to flag up as a yeah. It's something I'll flag up as one of those things you dream to do for AR5, because some of the land cover changes that we're predicting, for example, if the Amazon forest did disappear, would have an enormous impact on dust production. But whether we get there, I think is doubtful, the AR5 timescale. I'm going to run out of time here. This is just to show that the major uncertainty, the major discrepancy amongst the models is actually in the land response. And what you can see here for the entire period of the simulation is the fraction of the emissions absorbed by the land in a model where climate change doesn't affect the carbon cycle, that's the blue bars, and in models where it does. And generally speaking, apart from this model, you can see reductions in land uptake because of climate change. But it varies a lot in the magnitude. Some of the changes are really very small, some of them are very large. So you've got a significant range there in the land response to climate change. Now, that wraps up a load of things, because it's not just the physiology we've spoken about and its response to climate, but it's the climate change itself, and it's the regional climate change. So it throws back, it casts light again on the whole issue of regional climate change and how it differs amongst the models.
Can you point out which one are EMIX? Or which one are
Okay, these are EMIX. These are EMIX actually. Yeah. And there's another model now. There's a new version of the French model, which I'm going to show some results from, which has been added on, but it's not on this plot.
Is there any way to, like you just did this to the year 2000?
Yeah.
Is there any way to constrain that? I mean, is there any way to know that's under validation?
Yeah, that's basically what I had in here, Jerry. This.
So that's what.
Sorry. Okay. Yeah. Well, I should have made this clear. The black things are historical, right? So this is the historical carbon balance from the beginning of the run to 2000, and basically the models in this box fit the constraint.
Okay, so that's
and those models.
Observations of what the.
Yeah. So there's an estimate of. We know the CO2 increase very well. We've got a good estimate from Sabine of the ocean uptake. The big uncertainty with this is the denominator, which is the emissions. Now you think, well, we know the fossil fuel emissions very well, but what really produces this large range is the land use emissions. I haven't got the foggiest about those. And if we knew them, we'd be able to shrink this down and get rid of some models. Yeah. And then we could go and do something else.
You can do the fire emissions. Would the fire emissions make a large difference in those estimates? Or do you fold that in?
None of the models have got fire in them. Some of them could have had, but they disabled it. So in terms of the mechanism for the feedback, say from the land, you could argue that the feedback's too slow at the moment, because we're probably using soil respiration as a surrogate for other things like fire. I would say that means that it would be quicker if you had the fire in regions that are drying. Okay. So all CFOR MIPs simulate a positive feedback, which means a larger warming. And it also means if we start to think about stabilization scenarios, you turn this thing on its head, the emissions that are consistent with stabilizing a given CO2 are uncertain because of this feedback. And I'm just going to show you an example from the Hadley model, which sort of bounds it. Because remember, this is a model with a large feedback, and we compare it with the model without any climate feedback. This is for the WRE stabilization scenarios. So what we're seeing here is the annual CO2 emissions consistent with stabilization at 550 and 450 parts per million. And we've got two sets of curves here. The blue one is kind of what's been assumed before, which is what you can get away with if the carbon cycle is not being detrimentally affected by climate change. Still a very significant cut. The red one is what this would imply if the Hadley Center model were right. Okay, and we could put a range on here that's basically covering this range. The carbon cycle feedback says you're going to have less emissions for stabilization, consistent with stabilization, and the range is quite large because of uncertainties in this feedback. So I suspect as we get to AR5, well, I hope that we're going to turn this thing on its head and we're going to stop thinking about what happens if we do nothing and start thinking about what we have to do to stabilize at certain levels or avoid particular levels of change. If that's the case, then the carbon cycle feedback will enter through an uncertainty in the emissions. Right. I'm going to skip over some of this. Right, so there's a big uncertainty in the feedback, and Pierre's done a very, very nice analysis actually of the causes of this uncertainty on the global scale, which I've turned into this plot. I don't know how well you can read this, but basically what this is showing the impact of each of these processes, and I'll go through them in a minute, on the fraction of emissions that remain in the air. Okay, so in the absence of any carbon cycle processes, all our emissions would be in the air. We'd be talking about an airborne fraction of 1. Because the ocean takes up CO2, that's removed by somewhere between 20 and 30% according to these models. Because the land is responding to CO2, and we could argue that, but according to these models, there's a large range here, but also reducing the airborne fraction. So these are the negative feedbacks that still exist. They're carbon-carbon feedbacks. They're still important though, they still exist. So that's going on. These are the sinks that we already accounted for, associated with the response of the land and the ocean to CO2. What's new is these feedbacks, and these are all responses of land and ocean storage to climate. And what we've got here, can anyone read this at all? What we've got here is a range that comes from diagnosed from the models. And what we've got is soil decomposition response to climate. So this is this whole issue about the rate of respiration increasing with temperature. The response of plant primary productivity growth to climate, and you can see a very large range here, which is associated primarily with regional climate change uncertainties. The ocean response to climate, which is a smaller range, and physical climate sensitivity, right? So this is just to do with the fact we still don't know for a given CO2 what the climate change will be. And that's almost comparable to the biggest physiological uncertainty. So even if you're just worried about climate carbon cycle feedbacks, physical climate change is probably the second most or the most important thing to get right. And these things add up to this uncertainty in the climate carbon cycle feedback, these things here, okay. So we've got a rough idea by looking at these models how we rank the uncertainties. Yeah, Pete.
Why is the lower grade so broad when you've told us that over the historical record 25% or so has gone into the land? Why
Here.
Is that? Yeah.
Well, that was, essentially you'll have models that are here and here. Okay, there'll be models that are producing an uptake in the ocean that's within the bounds, and an uptake on the land that's in the bounds. That one's got a high ocean uptake, low land uptake, and vice versa. Okay, so does that make sense? Most of them fit within the.
Why can't you eliminate the lowish values there when you know that 25%
You could.
is
There's a joint constraint on these two things. That's true. The total, the sum of these three has to add up to that historical constraint I showed before. The reason there are error bars on it is because you get a choice about which one you use. We can't, from the observation record, we can't tell the difference at the moment to any great extent. I think you could rule some out. I mean, I haven't done that. This is the full ensemble, so we could. There will be some bounds on these, a joint constraint on these three things, and a joint constraint on the overall thing, which basically says you've got to fit the CO2 record. It won't be very strong though. It won't be a very strong constraint. How long have I taken? Feels like.
Another 10 or 15 minutes.
Have I? Better move on then. Right, so that allows us to rank to some extent the uncertainties. The response of the land net primary productivity to climate is number 1 uncertainty. The transient climate sensitivity to CO2 is number 2 on that basis. The response of soil or heterotrophic respiration to climate is number 3. But in terms of the CO2 increase, these are just related to the climate carbon cycle feedback. There's still a big range amongst these models in the amount of CO2 they take up, particularly in the ocean, even in the absence of climate effects. So we shouldn't forget that there's a climate carbon cycle feedback uncertainty, but there's also an uncertainty in just the response to CO2.
Peter, this might have been
Yeah.
related to the question that was just answered, and I didn't understand the response, but it seemed like on the previous slide that the response of NPP to CO2 was a huge bar.
Yep.
And yet that didn't make your top 4 bullets there.
No, it is there. Response of land NPP to climate, this one here.
Yeah, but not to CO2 per se, which just seemed like the light green bar.
Yeah, that's covered by the, okay, so this is, all right. What I'm mainly talking about here, George, is the uncertainty in the climate carbon cycle feedback, right? So that's just the top 4 bars, okay, because we've been mainly talking about that. Now, you're absolutely right that there's a big uncertainty just in the amount of CO2 that will be taken up, regardless of climate change. And there's this response, you're right, of course, and there's a response here. The NPP response to CO2 differs amongst models. Now, in that case, I'm pretty sure you can rule out some of those. Some of them have got a response that's too low compared to the OBS. Some of them have got very large responses, and I haven't done that yet. That's an error bar that I think will shrink significantly. Might be the only one. Okay. So what do we do next? One thing, and people have touched on this, we've got some time now to do more complete validation and use of observational constraints. Individual groups have done that, but we've not done it in a coordinated way yet. And then there are a whole load of things that we deliberately excluded from this first set of experiments that we've got to include if we're going to be taken seriously. And the first one, I think, is to model the land use in a consistent way. Sorry, the land use CO2 flux in a consistent way. And the related flux from forest fires. And I guess you're going to talk about this, so I won't say too much. This is just a data set of land use change. I guess this is in percent through, this is from PS, so I have no idea what it is. 1700, 1990, and what's projected for 2100 under this particular scenario. Very significant changes, which we've currently ignored. Okay, we set in most of the models a kind of anthropogenic land use mask, and then we leave it fixed. And as we go towards mitigation, the landscape's going to change, and we have to take account of that.
Peter, what's the actual scale?
I think it's probably percentage of land that's either pasture or agriculture.
I think this is a combination of the high pasture data sets and the Beans agricultural stuff over
Yeah.
the last couple of years.
I think Richard Betts put this together for C4MIP, and I think it's a combination of the two. So it's basically saying where are we forcing grasses where there might be forests, generally speaking. Now, I'm going to give a plug. Oh, George is gone. Actually, to do this is not trivial, because in order to deal with the land use, the CO2 uptake associated with land use, you have to deal with the age class distribution of forests in a way that most of these models don't currently do. And there are models that do that, but they're not within GCMs. And one of the models, this ecosystem tomography model, is a kind of rigorous way of doing this scaling up. You can't see this, but these are individual plots here, growing trees. And the key thing is, how do you get the statistical behaviour of that right without modelling every individual tree? People have tried the gap modelling approach, modelling every individual tree, but it's a disaster for application in a GCM. So you have to be a bit cleverer. And there is some really nice work being done on this, I think, that we're going to try and use a couple up in our model, which allows you to do this more like a fluid dynamics approach, you know. With fluid dynamics, you go from individual particles to fluid dynamics in a fairly rigorous way with a few closure assumptions. And you can do the same thing with veg dynamics. You just missed your plug. The other thing is forest fire. Now, this is a picture from Pierre. The latest version of Orchidée, which is the land surface scheme used in the French model, does have interactive fire, and other land surface schemes do as well. And this is obviously something that we'll move towards more and more. There's evidence that's quoted in the latest IPCC report that forest fires already increased in some regions because of climate change. So there is a potential feedback here from drying, regions that are drying and getting hotter, to forest fire emissions. More detailed ocean ecosystem models. We spoke a little bit about this. I've gone over that very quickly, but this is an example again from the French model of a move towards more resolving more components of the ocean ecosystem. Ocean ecosystem models are more rudimentary, in part because their components get advected around. I mean, we could do the trees in a fairly sophisticated way because you don't have this problem of advecting all these different species around. With oceans, every time you put in a new species, you get a trace of transport cost, which can become really crippling. So there's always been a tendency to be more simplistic with the ocean, but responses to things like ocean acidification and feedbacks from DMS, for example, require us to resolve this much better. And you'll see there was a point earlier about iron will appear in here. So potential feedbacks to iron, inputs from dust, for example. A number of groups are moving this way. Interactive nitrogen cycling on land, and I'm not going to go over this, but there are no nitrogen limits in these models, as we spoke earlier, and there have to be. And links to changes in atmospheric chemistry and aerosols. Now, just to summarise then, this is where we were at the time of the TAR with CO2 largely calculated offline. Some account taken of climate effects, but no regional climate change effects, and no consistency between the climate change and the CO2 uptake. And what we did for the fourth assessment report is C4MIT, which closed these loops here, but still dealt with the net land use as an input. So there's an inconsistency here in that we have land cover changes that are not consistent with the net land use. And what I think we're aiming for in the fifth assessment report is something more like this, where fossil fuels are our main driver of the CO2 increase. Land use change goes into the land cover in some way, and we consistently calculate the CO2 fluxes associated with that. What the models, I think all the models currently do as well, is to ignore the river flux of carbon, which takes carbon from land to ocean. And the reason for that is purely pragmatic. I mean, you can imagine if this thing is dependent on the land carbon state, you can't spin up your land and an ocean separately, and that is a disaster because the ocean carbon cycle has to be spun up separately to make this work. Otherwise, it's just too expensive. So this is the moment I've got this dotted because I suspect it will be very difficult to do that in a fully consistent way because of that, just that practicality of spinning up the ocean biogeochemistry.
What percentage of the CO2 goes into the ocean by everything?
I think it's a few tenths of a gigaton. Would you say, Kathy?
About
half, maybe half.
0.5 to 0.6.
So it means that the ocean, should be a net source of CO2, which we currently assume it's not, it's neutral, and the land should be a net sink of about half. Now, I'm not sure it makes that much difference, but if that flux were to change, and some people think it would, then it might. I mean, for example, if you're validating against flux measurements, and you saw a sink, but in reality it was just a transport here and outgassing from the ocean, you'd be getting it wrong.
Yeah, the global implications might not be so significant, but certainly the regional fluxes of where it's going to play out.
Yeah. Okay, and then,
One more
Yeah.
question. This is, well, it's not really tangential, but it's bringing in another issue of the increased concern about acidification of the ocean.
Yeah.
And I was just wondering how, what is assumed in the ocean models? I know nothing about this in terms of including changing chemistry in the ocean.
Well, they will by definition have acidification going on in these models. It's doubtful whether the current ocean ecosystem models will respond in a realistic way to that. So what I've done here is, these are the things that are in now. In addition, we will be doing better ocean ecosystem structure, which will help us do the climate change, but also this acidification issue, I hope. Do you want to add anything there?
Acidification is one of the top themes of the OCMIC,
Right.
Ocean Carbon Cycle Model OCMIC, Ocean Carbon Cycle Model Intercomparison Project. Which is another project on ocean.
Okay, so I've put in bold here ocean ecosystem structure as a much more resolved thing within these models, and fires, which we mentioned before. And then these become the inputs now. So these are the things that you'd want scenarios for. This iron dust deposition really should be consistent with the land cover change. And there will be models that do that. The Hadley Centre model's already got some experiments doing that, but whether you can get that for the whole community is another matter. So I suspect this will be an offline thing, but...
Do you know how the fire is going to be done? Is it simply a question of drying? Because you could have more sophisticated parameterizations, the convection above the freezing level, the amount of lightning.
Yes.
Is it assumed to be anthropogenic fires or lightning-induced fires?
The models try to deal with both. I mean, there is an issue about the balance between ignition sources, whether they're anthropogenic or climate related. And there seems to be, you know, it's almost like you can separate, a bit like with the water regime, you can separate into ignition limited regimes and litter limited regimes, I suppose. But yeah, you have to deal with both.
I think the current state is natural based on fuel load, moisture, typical fire modeling component, and with a view towards anthropogenic ignition in the future that will take into account.
There are some offline models that are already having a go at that, but you're right. There's always this lag, isn't there, between what goes in a couple model, what goes in an offline model, and what's actually being done at the process level. And we're always trying to bridge that. So one of the key things, this is the number one for me, is to do the land use change properly, particularly since I think next time round we'll be asked to assess mitigation options. I would imagine we would be. So doing that right requires consistent scenarios for land management into the future. It also requires that you do your land cover in a more sophisticated way so you can deal with these issues to do with age class. Links to chemistry. Now, if you're doing a fully coupled chemistry model, this would be a continuous line. We'd have nitrogen and ozone deposition affecting plant productivity, and I suspect there'll be one or two models that will try to do that, but I can't imagine them being standard AR for experiments. So I think we're going to need that consistent with this, consistent with that, and possibly consistent with dust deposition. And I think that's doable. I think we're on the way to doing that in these models. It won't make the uncertainties any smaller, generally speaking. No, I don't think it will. No, I mean, one of the problems is that as we move towards this Earth system approach, in the past we always sold things like increased resolution on reducing uncertainty. And now what we're doing is we've got a better assessment of uncertainty. It's much bigger than we said before, and that was always a bit difficult. So now we're almost selling on the basis of a better estimate of uncertainty.
Peter, maybe it's AR6 or AR60 or something like that. But the feedback of the climate change on the emission scenario itself, that's done, I guess, in these offline integrated assessment models to some extent.
Yeah.
But at some point, I guess, that's going to have to be coupled into these models as well.
I go for AR60.
But that will be a purely observational program.
Yeah.
If there's anybody left.
I mean, I think there's a bit of a hope there, though, that in the focus on stabilisation decouples bits of the system, actually. So, for example, if we said, well, what would we have to do to stabilise at 450? Then you take out some of the transient uncertainties from it. And then you come up with some sort of climate change, and the climate change could feed feasible mitigation scenarios. It could be the other way around when you're dealing with stabilisation.
You kind of see these problems where these land use scenarios that are proceeding despite the fact that the Amazon is being converted into a desert that are still being used for agriculture.
Yeah, well, we can deal with that. Sure, we can deal with that, I'm sure. And I think if, for example, the Amazon were to die, then you couldn't deforest it again. We'd be able to deal with that. And there will be a sort of, you can't kill the trees twice.
But then the CO2 emissions from deforestation that went into the scenario would have to be met somewhere.
Yeah, so, okay, but what we're proposing here is that this will no longer include the net land use, just the fossil fuel. And the land use emissions are calculated internally in the model. That's a key thing, and I know that's the sort of thing you're interested in doing. We've got to do that. Otherwise we get these inconsistencies.
But somehow it's like a demand for wood products, and the model gets to decide
Yeah.
where to actually meet that demand or something.
Yeah. Now you're beginning to scare me.
There is a broader issue of scenario consistency as you put the land use into the climate part, because many of the scenario drivers will be influencing land use patterns, so that they have to be forced somehow.
Yeah.
Right now that's done in the land use models and leads to both fossil and land use emissions.
Yeah, I don't know. Yeah, that's a tricky one.
Once you endogenize that, you have to be very careful about the consistency.
Yeah. How do we do? Well, maybe, I mean, that's probably what we're going to be talking about the rest of the week. But there are situations where a climate model would use a land use scenario that you produce and come up with a climate change that meant you could never have had that land use. And I don't, I don't know how to do that. Yeah.
Your question on your list, let's go back to the next slide.
Yeah. Yeah.
Yeah. I meant your list of, you seem to be listing the uncertainties.
Yeah, it's way back actually, but
oh, was it?
where did I put it?
Just on it.
Is that it? Yeah. This
Well,
one?
I could just say it's easier that although there's, you know, a wide uncertainty of the numbers in positive feedback, as you say, there's close to zero uncertainty about the direction of change. So that we're definitely talking about increased airborne fraction.
Well, I've got 11 models, none of them produce a reduction in the airborne fraction.
Right.
Yeah.
But the agreement of the well-known agreement of models is not the same thing as saying that we got them right. So I guess.
Yeah. Okay, but they've not. I mean, when we go through another intercomparison experiment, they will converge, right? To the point you were saying earlier, David, people will try to make sure, they'll, in the absence of data, they'll think, I really want to be in the middle of the pack. In most cases, they will. And if we could, we would. But we don't think it's right. So the models haven't had that yet. So the fact that they all produce a positive feedback, even though in some cases it's small, I think is quite a strong result, actually. There's no reason why they could have. Some people would have said, well, it will go the other way. We'll have so many forests in the boreal region that we'll get a carbon sink. So we're trying to bring that out in the IPCC chapter, that quantitatively we haven't got a clue, but qualitatively we have.
So are you going to use a likely statement? Talking likely, very
I don't think I did. What did I say, Guy? Absolutely true, probably.
Absolutely true. Whoa.
Extremely high confidence.
That's right. I'm going to just summarise because I've gone on too long. Okay. First generation climate carbon cycle models all suggest that climate change will increase the fraction of CO2 emissions that remain airborne. All of them, 11 out of 11. But there are major uncertainties in the size, between 20 and 200 parts per million by 2100. So at the upper limit, this is a showstopper. At the lower limit, if the first model had been 20, the rest of us wouldn't have bothered doing it, frankly. So I apologise for anyone who's gone up the garden path, but I think there's something at the end of the path. This uncertainty also has impacts on the emissions consistent with stabilisation at a given concentration. In some ways, I think this is more important, because this is about stabilisation scenarios and what you have to do to reach stabilisation. And so reducing the uncertainty is even more important. In AR5, I think the models will evolve partly because they'll have more time to do validation, but they'll also include things we know should be in there and we just didn't do because we didn't have time to do them or because we were developing the modelling. Interacting calculation of net land use emissions is the number one. More complex ocean ecosystem models to deal with things like acidification. Interactive nitrogen cycling and nitrogen limits on the land, and possibly riverine carbon fluxes from the land to ocean. I'm not sure about that one. Makes the experimental design really hairy, so we may end up backtracking. And I think this places new demands on the driving scenarios that we need, particularly in terms of consistency, because before, someone just gave us a CO2 scenario and we said, well, all right, doesn't really have to be right, we're all using the same, that'll be fine. But now we have to have scenarios that are consistent across the board, which is tough. So nitrogen deposition, ozone concentration, land use and land management, and dealing with the possibility that the climate change itself affects those things like the patterns of land management. And I think we're going to need a week to discuss that. And that's it, yeah.
So there's no more burning questions. You have a burning question?
It's not about forest fire.
I mean, normally you, like, let me try and get this right. You haven't said anything about the variations between the climate sensitivity of each model and that no carbon cycle is in different models. But if you calculate climate sensitivity by just doubling CO2 and with a mixed land ocean,
yeah.
you do that with the land components before and the land component that you've used.
Yeah.
Are those climate sensitivities radically different for the Hadley Center model?
It depends on, in the Hadley Center model they would be different, but it's nothing to do with the CO2 because of course when you double CO2 you take out the carbon cycle feedback, right? I mean, So there's no way in which the land can affect the CO2 concentration. In the Hadley Centre model, it's partly because of vegetation change. And if you ran them to equilibrium, you get a very different climate sensitivity because the boreal forest would go a long way north and produce an albedo feedback. Even if you didn't move the forest, in that model, in one or two others, there's stomatal closure because of increased CO2, reduced transpiration in response to CO2, and that has an impact on amplifying the warming over land. But that's not common to all models. I mean, I think it's a real effect, but it's not in all the models.
But by running that double CO2 experiment, can you get an indication of how sensitive your model will be to the land changes?
Yes, you can. I mean, you could do it. You'd have to be careful with the vegetation dynamics because of the timescales issue. You know, if you give the forest infinitely long, it will go a long way north in an equilibrium sense. If you run it in a transient, it won't move very far. So they'll give you slightly different answers, and the range would be even bigger because of that. Because some models would put forests right up near the pole. But yeah, we do need metrics like that. There's talk of.
But that double CO2 experiment, its equilibrium time could be a lot longer. That's what you're saying. One of the reasons it's used now is if you just have a mixed aeration, you've integrated 50 years of your
well, yeah. So in some of these vegetation models, because they've got long spin-up times, they have a sort of accelerated approach to equilibrium. You sort of like ocean spin-up type approaches, where you say, okay, let's make the time derivatives big, so that we get there quicker. So they've got some techniques to do that, but yeah, it would take a long while to do it, and it would be a different response, a very different response. That's one of the problems, is that the transient response, the equilibrium response, has no real meaning in the carbon cycle. I don't think.
Okay, thanks.
Yeah.